Let's blow it up a little. Chemical kinetics. All your objectives, and they're the pre-lab questions. So what do we have? 3 of them? Yeah, 3. Okay. Come on in. So the first question is, if you have a container of household bleach, and this used to be the normal concentration for bleach, 5%. Now they've got much more concentrated, 6. I've seen 7, 8%. But the procedure for answering this question works no matter what the percent is. Your percent, I think, for the lab is going to be 6%. So 5% by weight. So this is 1. If it's 5% weight, that means 5 grams of sodium hypochlorite per 100 grams of water, 100 grams of solution. 100 grams of solution. That's what that means. The question is, what's the molarity of this solution? And you need to be able to calculate that, because when we write the rate law for this reaction, you're going to have rate equals some rate constant times, let's see, we got bleach and blue. I think it's blue number 1. So it's blue number 1 to the n power times sodium hypochlorite to the m power. That's the final form of the rate law that you're going to determine with this experiment. So we need to know the exact concentration here. We're going to use, for blue, instead of concentration, we're going to use absorbance units. Because it's a blue dye, we can detect its concentration simply based upon absorbance. So that's what we're going to use for this term, but this term has to be molarity. So that's why you need to be able to calculate this. Okay, so we're going to calculate molarity. If we're starting from here, where are we going to end up? Moles of sodium hypochlorite per liter. Right? That's where we're headed. So, and this is in mass. That's where density comes in. Grams per milliliter. So this says so many grams, what is 1.08? 1.08 grams of solution per milliliter of solution. Right? That's what that means. So we got rid of grams of solution, but now we got milliliters and we need liters. Okay. So 1,000 milliliters per liter. That gives that this is liter of solution. Still liters of solution. I'm going to run out of space, I think. So remember, when you're doing unit conversions and you got more than one unit in that you're starting with, do one at a time. So we took care of the denominator. We converted it into liters of solution. Now we need moles of sodium hypochlorite. That many grams of sodium hypochlorite. If we want to cancel grams and liters with moles, guess what that is? Molar mass. What's the molar mass of sodium hypochlorite? Is it given? We have to calculate it. Okay, sodium hypochlorite. Sodium is 23 in 2 decimal places. Grams per mole. Excuse me. Yeah, mole. That's right. Oxygen is 16. Chlorine is 35.45, I believe. Yep. So we add those together. 11, 15, 5, 6, 7. 74.45 grams per mole. There we go. So that takes care of grams and leaves us with moles. Moles per liter. That's the thinking part. Rest is number crunching. So let's see what we've got. 5 divided by 100 times 1.08 and times 1,000 and divided by 74.45. So that's 0.725. 0.725 molar sodium hypochlorite. Okay. Now, your solution is, if it's 6%, you just put a 6 in there, and then you need to know this one. And I think for 6%, it's 1.09. So 1.09 would go in there, and you just do the same crunch and get a value. That's right. Okay. Number 2. I want to leave that up there for now, unless I need the room. Number 2 says, how many grams per liter of sodium chloride are required in order to prepare a solution with a concentration equivalent to the solution in question 1? All right. So in this case, we're starting out with 0.725 molar sodium hypochlorite. We want 0.725 molar sodium chloride. Sodium chloride. Now, why do we want that? Well, if you're familiar with the method, we're going to do a degradation of the blue dye using bleach with 2 different concentrations of sodium hypochlorite. Okay. What we want to do is maintain the ionic concentration in the solution. If we just put a certain amount of sodium hypochlorite in there and measure the absorbance as it gets lower and lower over time, and then we just put half of that in there and say just made up the difference in volume by an equal volume of water, that would bias our results. I don't know which way, but the ionic concentration would not be the same because you'd only have half of the sodium and the hypochlorite ions. So we're going to balance it with dilute to go to the half strength. We're going to dilute with a solution that's equal in molarity, but sodium chloride, which has no bleaching properties, to maintain the ionic strength. Okay. So we need to know how to mix up a 0.725 molar sodium chloride solution so that we can put an equal volume of sodium chloride with half of the original full strength amount to give us a half strength sodium hypochlorite. Okay. Because we need to know the decolorization process for both concentrations of sodium hypochlorite. Now, do you remember why we have to do that? Because we studied, well, I erased it now. We studied 0 first and second order equations in terms of only one reactant. It's like a decomposition. But now we've got a reaction where there are 2 reactants. That complicates things. If we let both of them vary, which one's responsible? So what we do is we jack the concentration of the bleach up so high that during the reaction, it doesn't change. And that way, maybe I better put it up here. So the rate is equal to some K value times the blue dye, and that's going to be in absorbance, 1 to the N, times sodium hypochlorite concentration to the M. Well, if we're going to make this so high that it's constant, then we can dovetail this constant value with that constant value. And then our new constant, K prime is equal to this is the one we're after. But for now, we're going to combine it with this one. Okay. So now we can write our rate equation like this. Rate for the full strength hypochlorite is K prime times the blue. Now we have one variable, and we can assess that. But then we have to do it for, well, you can use any strength, but we're going to use half strength. And that's equal to, and this is K prime for the full strength. It's going to be different for the half strength times blue to the N, not M. Okay. Now these values, these N's should be the same. And then we can use that information to work our way back to this one. Once we find out what, well, this K prime depends on whether this is full strength or half strength. So when we do half strength, we need to dilute it with something that gives us the same number of ions. Right? Instead of sodium and the hypochlorite ions, we'll have sodium and the chloride ions, which will not bleach, but it will give us the same ionic strength, and the environment will be the same for both reactions. That way we don't bias our results. All right. So we need to convert this to how many grams per liter of sodium chloride we need. So this is molarity, which is what? This is moles per liter. Let's just do that. Moles per liter. And we've already got a liter, right? So we don't have to change the volume because the question says how many grams per liter. We just need to change this to grams of sodium chloride per liter. So moles, grams. So what's the molar mass of sodium chloride? Well, it'll be 7545 minus the oxygen, won't it? Because we had oxygen in there before. So we just subtract 16 from that. We do that in our head. 8. 58.45. Add 16 to that and see if it's the right answer. Yeah, that's right. Okay. So now that gets rid of moles and leaves us grams per liter. 0.725 times 58.45 is 42.4 grams of sodium chloride per liter. Now, we don't need a liter. So if you're actually going to make it up, if you're doing the experiment by yourself and there's nobody else, you can make 100 mils easy. You could even make 10 mils, probably be enough. But if it were 100 mils, how much sodium chloride would we need? What's the ratio of 100 to 1,000? It's a tenth, right? So you take a tenth of that, 4.24 grams in 100 milliliters. That'll give you the concentration you need. Okay, 3. Let's finish 3. Okay. What is the percent sodium hypochlorite by weight for a liter of bleach that is 0.8 molar sodium hypochlorite and has a density of 1.09 grams? Okay, so this is another unit conversion, but we're working backwards. We want percent by weight or by mass. So we're actually working backwards. 0.8 molar, 0.8 moles sodium hypochlorite per liter. Okay. All right. Let's do the volume first. No, let's do the mass. Let's do the mass first. So we got to reconvert this sodium hypochlorite from moles to grams. And there's your conversion factor, 74.45. That gets rid of moles. Now we've got grams of sodium hypochlorite. We need grams of, or 100 grams of solution. So 1 liter of solution, we need mass of solution because this is mass per 100 grams, grams per 100 grams. So this is going to be, let's convert that to 100 milliliters. I don't want to do that. Now let's just convert it to milliliters. Yeah, let's convert it to milliliters. Liters, 10 to the third milliliter. That gets rid of this one and that one. Now, convert that to mass. Right? Convert milliliters to mass of the solution. And here's where we need the 1.09 grams per milliliter. So this is a different concentration. 1.09. We want to get rid of milliliters of solution. Here. This is solution. And make grams of solution. This is 1.09. Like that. Okay, that gives us grams of solution, but we need 100 grams of solution. Right? So we just multiply by 100. Now we can, it's kind of like, yeah, it's the same as percent, right? Something divided by something times 100 is percent. So 0.8, 74.45 times that, divided by 1,000, divided by 1.09 and times 100. And I got 5.46% bleach. Okay. Let's see if that came in where I expected it to be. Yeah, what where? Okay, so that's your 3 pre-lab questions. And do we need any more background on the procedure? I got to this point. The reason we're going to do 2 separate reactions, and there's an explanation in your copy of the lab that describes what to do with the data. Follow-up calculation. This first one is how to get the molarity of the bleach. And then half molarity, which is you divide by 2. And then this one is calculating the true K. Okay. It'd probably make more sense once you got numbers. Yep. But eventually, you want a value for this one. You can put either blue number 1 or you can put absorbance, right? A for absorbance. And then sodium hypochlorite, you're going to have a value here, here. You won't have a value here. These are variables. You'll have a value there, and then just say rate. So you need a value here, here, and here at the end. That's what we're looking for. And I will say this. Since we're working on this one from our 0, 1, and second order graphing capabilities, we detect this one as either 0, 1, or 2 based upon the graph. Which one gives you a linear graph? The raw data, natural log, or reciprocal. Find out which one gives you the straight line. And that'll tell you what the blue exponent is. It'll be a whole number, 0, 1, or 2. Then when you go in and calculate this value, it doesn't have to be a whole number. Right? It can be and it probably will be a fraction of some kind, a decimal fraction, decimal number.